Hello everyone, welcome to another lecture for drug delivery engineering and principles. We have been talking about now nano and microparticles, and we defined some of the things, and we were talking about the synthesis methods. So let's get started. So just a quick recap of what we learned in the last class itself. So as I said, we talked about particles, both micro and nano. Some of the definitions as to what are micro, what are nano, what are the size limits and things like that. Then we talked about that these particles have advantages over, let's say, an implant system, where these can be used for delivery to intracellular regions. So you can have a cell. Usually if a drug is hydrophilic or charged, the drug is not able to go through. If let's say drug is charged, it is hydrophilic. However, once you package it into a particle and encapsulate this drug inside, these cells have endocytosis mechanisms through which they can take up these particles with drug, and that is how you can deliver things intracellularly as well. Then we talked about proton sponge effect. So what was proton sponge effect? So again, zooming into this, if we have, let's say, a vesicle containing particles, these vesicles will have to burst for the particles to come out into the intracellular environment, because we do not really want to deliver most of the drugs to these endosomes and lysosomes, which are very sort of toxic to these drugs. So for that to happen, we use something called a proton sponge effect, and what it is you make your polymer with lots of tertiary and secondary amines. And so what they do is they keep on absorbing H plus ions that are being pumped into these endosomes, and does not let the pH to drop. And because of that, the cell keeps on pumping more and more H plus and other ions into these vesicles, causing an osmotic pressure and the water to start moving in because of this osmotic pressure, and ultimately the vesicle then bursts. Then we talked about few of the particle synthesis methods, both chemical and physical. One last thing that we were talking about before we left in the last class was solvent evaporation single emulsion method, and what essentially we do in this is you have, let's say, your polymer being dissolved in let's say some oil phase, and which contains your polymer plus drug, and then what you essentially do is you add that to an aqueous phase and give some energy that results in emulsion being formed, which is essentially the separation of this oil from the aqueous phase, and you let the oil slowly evaporate out. Maybe it is highly volatile, and that essentially causes the sort of precipitation of these polymers that were present in the oil phase to form particles encapsulating the drug. So we are going to continue further today in our particle synthesis methods. So the first thing, I mean, we talked about it briefly in the last class too, but emulsion formation is one of the key steps which leads to the synthesis of these particles. So what is emulsion? Emulsion is nothing but if you apply some mechanical energy to disrupt the interface between two phases, it causes the droplets to form. So let's say if I have this beaker, and if I put both the oil and the water phase, so what will happen? They will phase separate out, right? They do not really want to interact with each other. So you will have water or aqueous phase separately from the oil phase. Again, depends on which one is lighter. So typically oil is lighter than water, so it will float above water. However, what happens if now I come and give some energy to it? So what will happen, because of this energy, I am like forcing this oil and water to mix, but the oil and water does not really want to mix. So what will eventually happen is, instead of mixing, there will be a single phase depending on which one is the higher amount, if water is in excess or oil in excess, and the other phase, the oil or the water, will essentially tend to form these droplets. And these droplets are being formed because of this energy. We are sort of breaking this interface again and again. So the more energy we will give, the smaller these droplets will be, and these droplets will then tend to form. So, this process is nothing but it is an emulsion. So, now what will happen if I stop right now, let us say I stop this propeller, initially it was rotating, but let us say I stop this, what will happen is because these droplets are continuously moving around and they do not really want to interact with the water interface. Let us say if this is oil and this is water. So, these do not really want to interact, they want to minimize the contact with the water. So, what will they will do is they will start to coalesce. So, they will mix and essentially go back to the initial separation. But this is something that we do not want, right, because ultimately all of these individual particles that we had initially is what is going to give us the particles. So, to prevent that, what is done is we add these surfactants or sometimes they are also called as stabilizers to these mixtures. And so, what that does is that then it does stabilizes. So, if I now zoom into one of these droplets, so this surfactant, and what a surfactant is nothing but an amphiphilic molecule which has parts which are both hydrophilic and hydrophobic. So, what will happen if let us say this is oil, this is water. So, what the surfactant will do is the hydrophilic part will try to interact with water and the hydrophobic part will try to interact with the oil. So, it will essentially form this barrier between the oil and the water, right. And so, what this does is it sort of stabilizes this droplet, because now technically speaking the oil is not in direct contact with water and neither is the water contact with the oil. So, in that way these droplets are much more stable and they do not tend to mix with another droplet. So, this will not happen once the stabilizer is present. And once we have that, the emulsion size and the stability will directly affect the size and the internal architecture of the particle formed. So, bigger is these droplets that we have, the bigger is the particle. If this is higher, then eventually the particle will also be bigger, and that is because whatever polymer is there will essentially collapse and there will be more polymer in the bigger droplet. So, that is how you will sort of determine the sizes of your particle. So, if I want bigger particles, what I will do is this mechanical energy that I am giving, I will decrease it, right, because if it is decreased then you get bigger size droplets and those will eventually result in bigger size particles. And if I want smaller and smaller particles, I will continue to increase this mechanical energy till I achieve that size range that I am desiring. Okay. So, what can be the sources of these mechanical energy? So, there can be several of them. So, it could be just simply shaking, you just hold the beaker in your hand and just sort of keep on rotating it. You can give it a lot more energy, you can put a magnetic stirrer bead in that. So, this is very commonly seen. So, you have a magnetic heat plate, it has some kind of a magnetic rotation that is happening and you keep a magnetic bead here. So, this magnetic bead will also rotate, giving energy in the system. So, these are somewhat some low energy based things that we talked about. Then you can have high speed homogenizers that can that have a propeller in them, and these things can spin at anywhere between 1000 rpm to 20,000 30,000 rpm, and that can give a lot more energy to get smaller sizes, or you can give something like an ultrasonicator which will then send out these very strong mechanical electrical forces that will result in very small droplets. So, all of these methods you can then use to sort of vary the size range that you are looking for. So, we talked about the single emulsion already, we are going to now take this forward and talk about double emulsion. So, the problem with the single emulsion is that you can only get hydrophobic drugs in there, because let us say if this is my particle that is formed of a single emulsion. This particle is completely covered with polymer, right, and then this polymer, as we talked about, let us say in case of PLGA, this polymer is fairly hydrophobic, which essentially means that the drug that is going to stay in here has to be hydrophobic, right. If it is a hydrophilic drug, then it will not tend to stay in, but it will never actually go in the oil phase, it will always be remaining in the water phase, which is outside, and you will never get that encapsulated. So, so this double emulsion is sort of a modification to the single emulsion process, which allows you to encapsulate both hydrophilic and hydrophobic drugs, and let us talk about how we actually do that. So, to do that, what we have is we have aqueous drug solution, which is typically water, or you can have water and oil. So, in this case you have, this is an oil phase, you have aqueous drug that you add a little bit of it, let us say if this was some 10 ml, then you add let us say 1 ml to that, and then you homogenize it. So, what will happen, you will get a very similar thing that happened in the previous case, you will get an emulsion, single emulsion. In this case the single emulsion is the other way around. So, in the previous case we had oil in water, in this case now we have, since oil is in excess and water is in limitation. So, let us say if this was 10 ml and this was 1 ml. So, what you will have is you will have predominantly a small water droplets in the oil phase, which is the PLGA phase, and so that is single emulsion there, which is called water in oil. Then what you do is, so this is essentially just a zoomed in image. So, you have drug in the aqueous water core, you have this the polymer in the organic phase, this could be DCM, this could be chloroform, and so that is how you stabilize the first sort of your emulsion process. And then you take this whole first emulsion and let us say you dump it in 50 ml water phase. So, now what is happening, and now you have now increased the water content in the whole mixture, and now if you give energy to this, right. So, now you are basically taking that whole thing and giving it energy now. So, what will happen is these droplets have already, the initial first ones have already stabilized, right, these are all stable. So, what will happen now is these will result in sort of a double emulsion. So, earlier we were talking about we have water in oil, now we have water in oil in water, right. Now, this water is in excess, but this water is stabilized within this oil. So, you will get something like this, where you have, this is an aqueous, so in this case we have used polyvinyl alcohol, which is a stabilizer or a surfactant. You have an inner aqueous phase, which is the same as this guy, and then you have these blue oil phase has been pinched off into smaller droplets. So, essentially you have, this is oil, this is water, and this is water as well. So, now what you will get is you will get a hollow particle. So, instead of getting a solid particle in the single emulsion case, now you are getting a hollow particle. So, then all you have to do is let this oil phase to evaporate. So, DCM or chloroform both have both are very volatile and they will evaporate fairly quickly. Then you will get microspheres, which you can then use centrifugation by pelleting and then lyophilize them to dry them off, and that is how they will typically look. So, if you notice here, there is a sort of a shell. So, this is in an SEM image, one of the particle or two of the particles have broken down. So, what you can see is that there is a shell and then inside it says hollow. So, this is the inner water phase, this was what was the oil phase, and then of course, the outside is all water, which you of course pelleted here. So, that is how you will get sort of a hollow particle. And why is that advantageous? Because now since this is initially water phase, you can have hydrophilic drugs getting encapsulated. So, here is sort of how this is going to look. So, you will have a PLGA shell which is surrounding a hydrophilic drug. So, that is how you can get a and then of course, the PLGA shell can still be used to encapsulate hydrophobic drugs, right, because any drug that I have which is here can also be hydrophobic. So, that way you can have both hydrophobic drug as well as hydrophilic drug being present in the same particle. And so, just some more terminologies. So, the internal aqueous phase is what is called as the one that you had added initially. So, whatever was here, this is called internal aqueous phase, right. Whatever is here, it is called the oil phase. There is only one oil phase in this case, and whatever was in the final larger water volume is called the external aqueous phase or the continuous phase. So, let us talk about some of the key concepts from this double emulsion process. So, again as I said, it is generally used if you want to encapsulate water soluble drugs. So, if you are looking for drugs that are only going to be hydrophobic, then the single emulsion is the best way to go about it. It is simpler as well as you get a lot more area or volume in which you can encapsulate your drug. But if you want a water soluble drug, then you want to create some sort of a cavity where the water phase can reside, and that is where your drug will get encapsulated. So, these produces micro and nano capsules. So, unlike so this is some sort of a reservoir system or hollow particles that we are talking about. So, unlike your single emulsion where the particles will be completely uniform inside, this is going to be more of a capsule sort of a scenario where there is a small shell surrounding your empty cavity. So, as I said, this emulsion could be called as water in oil in water. So, typically you will find this written as W/O/W, and again this is not really limited to this. This emulsification could also be water in oil, right. I mean it does not have to be the external phase has to be water, it is just that you just have to ensure that between the two oil phases the polymer is only soluble in one of the oil phase. So, that way you can also make sure, although this is not really used in any of the biological sort of scenarios, because the particles that you want has to be able to survive in water, has to be able to go and be stable in water. So, typically the external phase is also usually water, but you technically can have a two immiscible oils being used here as well. So, an example to that is in the first emulsion could be re-emulsified in hexanes or pentanes, and the PLG is insoluble in all of these, right. So, if you essentially what we are talking about here is you will have water, you will have a shell of oil after the first emulsion, after the second emulsion, and let us say this oil is DCM. Now, if I know that the DCM and hexane are immiscible, that is they are not going to mix, then what I can do is I can add this to a solution of hexane which will not solubilize my PLGA and which is not going to mix with DCM. So, this can technically still result in a emulsion as well as particles. The only problem is these particles will tend to agglomerate in water, right, because these are stable in hexanes, but once you put them in water they may not want to interact with water, whereas when we had PVA in the water, the PVA had coated these particles and had kind of stabilized these particles, but this may not happen in case of hexane. Right, and then the second method is often used to prevent diffusion of the drug out of the external aqueous phase. So, so this is going to result in a very more pronounced single emulsion process. So, the drug has to be insoluble or less soluble in the oil too also, right, because initially when we are talking about these emulsion process, there is always, this is still liquid, right, this is still liquid oil 1 and then oil 2 and then water with drug. So, if let us say the drug is soluble in oil 2, then the drug will tend to slowly diffuse out into the oil 2, but if the drug is insoluble in oil 2, it will not really tend to go there. And so, this will still you have to make sure also that whatever drug you are encapsulating is insoluble in oil 2. Okay. So, a little bit more about the solvent evaporation process. So, again as I said this is what you get, you have these hollow particles that you will get with a polymeric shell surrounding it, right, and then external is of course in biological applications will be water. And then you can use various kinds of techniques. So, this is an SEM image, you can use other techniques, you can determine the particle size by dynamic light scattering using Coulter counter or other similar instruments, and you can get some sort of an idea as to what is the size. In this case since this scale bar is about 20 microns, we can say that the average size here might be about 5 microns, but you can then again vary that by changing the energy that you are providing to the system. So, what are the different parameters that are going to affect these particles? So, of course, the first thing is what polymer you are using and what is the molecular weight. So, that is going to have a profound effect on first of all whether it is hydrophilic, hydrophobic, and then also whether what is the thickness of the shell, how stable it is, how fast it degrades, all of that will depend on the polymer you are using. And then of course, the polymer concentration in the oil phase. So, the more concentration you have, the more closely it will pack. So, all of that will determine what sort of particles you get. The type of drug, so that is of course very important because that will determine what method to use. So, you can whether it is hydrophilic, hydrophobic, whether it is liquid or some suspension. So, depending on that, so if it is hydrophobic, you only will go with single emulsion. This is of course in case of PLGA. If it is hydrophilic, then you will have to go with double emulsion. So, all of these are important criteria that you will have to consider. And then of course, what organic solvent you are using and what is the polymer solubility, that will determine how much polymer you can actually concentration you can get in that particular solvent. So, all of these are important parameters. What about the type of amount and surfactants? Of course, you would want to add some surfactant to make sure that these particles are stable and are fairly not very polydispersed. So, and then how much is the amount of it? So, most surfactants you will find in literature is also toxic. So, if you add too much of that and you are not able to wash it off, then your particles may not be compatible with your biological assays. So, all of that needs to be sort of optimized, and you need to use surfactants which are fairly biocompatible as well as their amount is also limited. So, amount should be enough so that these particles are stable, but not too much that they become toxic. And then what is the ratio of your internal aqueous phase to organic solvent? So, that will determine as to what is the size of your particles as well, how much energy you need to give. Again energy by far is the most important criteria in terms of determining the size. So, if you have very high amount of energy being given it, you will have a decreased amount of particle size as a result, whereas if your energy is lower, then you will get a bigger size particle, and that is very easy to see, right. If you do not give any energy, you get a huge block of PLG, right. I mean, if I do not give any energy and I have these water and oil phase separate out, and if I let it evaporate, then eventually what I will end up with? Eventually I will end up with a block of the polymer, right. So, so this is going to be a huge block. This we are talking about centimeters and centimeter length scale, and the more energy we will give, the smaller this will become. So, it is easy to remember. And then at what rate we are evaporating it out, what temperature we are evaporating out. So, when we say evaporation, this is we are talking about the oil phase itself. So, the oil phase will have different evaporation rate at different temperatures and pressure. So, depending on all that, you will have a different amount of precipitation of your polymer happening. So, that will also affect the particle size. So, again how much volume is there, what is the temperature at the time of evaporation. So, a little bit more on the solvent extraction or the removal method. So, most solvents that are used to dissolve the polymer have some solubility in water. So, actually how does it happen, how does these things able to evaporate through the water. So, that can only happen if they have certain solubility in the water. And so, what do we mean by that? So, so for that to happen, the emulsion has to be added to a very large amount of aqueous solution with or without the surfactant, and the volume should be large enough so that the organic solvent is actually soluble in the water phase. So, now what I am saying is, initially if you look at the system after the emulsion has been done, what we are saying is, let us say for a single emulsion, this is your oil droplet, and then of course there is some shaking going on, so it is being continuously moving around. But to be very, the evaporation can only happen from the surface. So, but the surface is here is water. So, for this oil to evaporate, there has to be some oil present on the surface, right. And so, for that to happen, what happens is the oil will have some solubility in water. So, let us say the solubility is very low, let us say it is only about 0.001 milligram per ml of water, right. But then this is there, and then as more and more oil is going to evaporate, more and more oil is going to come out from here and dissolve in water, and this process is going to continue. So, for effectively, if you want to evaporate everything, you want to make sure you have a very high surface area at this interface, so that more and more oil is getting evaporated. So, that is what we mean by the solubility of the oil in water. It is low, but then it is there and it is highly volatile, so it is going to continue to facilitate that process. So, again the solvent is rapidly extracted out of the polymer phase into the external continuous phase, right. So, this is the external continuous phase. So, because it has certain solubility and the solubility decreases or the amount decreases as it is evaporating. So, to compensate for that, more and more oil comes and gets dissolved in the external aqueous phase. And so, what this does is eventually let us say you had, so if I focus now only on the particle. So, this is oil. So, slowly and slowly, so let us say this is a certain volume V ml of oil in here. So, what is happening is slowly and slowly this V is now decreasing, it is becoming V by 2, it is becoming V by 4 and further so on and so forth, but the amount of polymer that is there in this amount is actually constant, right, that cannot evaporate. So, that is now condensing more and more chains are coming closer together, and eventually it starts to form this thick particle. So, the thickness of the shell will be determined on what? Will be essentially determined on the polymer itself. So, how much polymer, what is the molecular weight, all of this will determine the thickness of the shell. The internal particle structure, porosity, etc. can be altered. So, if I do it very slowly, I will get a very hard particle, but if I let us say evaporate this oil phase very quickly, these polymer chains may not have time to move around and sort of make a very condensed structure. So, what will in that case what will happen is, instead of getting a very condensed structure, you may have lots of polymer at one phase, lots of polymer at other phase, and then very little polymer in another. So, you may get like these pores and sort of these holes into these polymer structure. And then finally, one of the disadvantages of this system is it requires very large volumes. So, and the reason for that is, if you want to evaporate out, you need to, and especially at a reasonable time frame, you need to make sure that it has a lot of surface area through which the oil is evaporating. So, just to give you an example, DCM has a solubility of about 1.5% weight by weight. So, to extract 10 ml of DCM rapidly by this process, the volume of external phase will come out to be greater than 660 ml, right, and that is extremely large volume. So, now you are talking about very high volume that you need to now precipitate or sort of centrifuge to collect the particles, you need very large reactors and all that. So, that sort of poses quite a lot of limitations onto what you can do. Okay. So, we will stop right here for this lecture, and we will continue the rest in the next class. Thank you.